So we have talked about what an extrema is, which is a minimum or a maximum, and I've alluded to the fact that there are different types of min and max, which is an absolute min or max or a relative min or max. So in this section, we're going to focus on the relative extrema, and we'll talk about what that means, and also critical numbers and what those are, because that's going to come into play. So this is a graph of the function f of x equals x cubed minus 3x squared. And notice we're not giving the interval, so this is an open interval question. There could be arrows on each end of this graph, so we get the idea. And we just looked at a quartic graph that was very similar, and we said, hey, there's no min or max, because, well, on that question, there was no max, because it goes on forever. So similarly here, this goes on forever positive, and this goes on forever negative. However, if we're looking at relative min or max, it's essentially where it's higher than everything around it or lower than everything around it. So a hill or a valley. And mathematically, what we're going to think about is when the hill or valley is smooth and rounded, if I were to draw a tangent line, say at this point, it would be a nice horizontal tangent line. If I had something that looked more like this, which is an absolute value function, this guy would be the minimum, the relative minimum, or actually the absolute minimum as well. But notice I couldn't draw a tangent line at this point. Obviously it's not differentiable because it's a sharp corner, and so it is not differentiable at that point. So either of those would represent a relative min, relative max, or sometimes an absolute min or max. So again, here's the formal definition for relative extrema, and that is essentially saying if there's an open interval containing C, on which f of C is either a maximum or a minimum, then f of C is called the relative maximum or relative minimum, respectively. Or you can say that there is a minimum or maximum at the point C, comma, f of C. If you have more than one relative maximum, it is called a maxima, or they are called relative maxima. That is the plural form. We don't use local very often, but if you see it, that's essentially what it's saying, is a local min and a local max. So again, we're just looking at the pictures right now and saying, hey, it's smaller than everything around it, or greater than everything around it. So again, back to our original picture, 0, 0 would be considered a relative maximum because it is the maximum on some open interval. So I've given you a sample open interval, so from -1 to +1, it's the largest value in that interval. You don't need to really come up with the interval. We're just saying, hey, if I have some sort of neighborhood around my point, it's the largest. Or if I have some sort of neighborhood around my point here, it's the largest. Or sorry, the least. So you get the idea that right now, before we look at it mathematically, all we're doing is looking at our graphs and saying, hey, look, there's a peak here, or there's a valley here. So obviously, this being a calculus course, we'll want to find the mathematics behind the relative min or max, as opposed to just graphing things and looking at their pictures. So we're going to start to segue into that, and here's our first example. Keep in mind, though, the big picture, where we're heading to. We're trying to find where we're going to have a min or max without having to graph it. And we talked a couple of slides ago about the fact that if it's a min or max, it's either going to have a nice horizontal tangent line, or in the case of a graph that has sharp corners, it would be not differentiable at that point. So that's what's going to lead us into finding critical numbers, because critical numbers will be the x values for where it's either not differentiable or has a slope of 0 on the tangent line. But again, I'm getting ahead of myself. I just wanted to let you know where we were headed. But for now, let's just take it a little bit at a time. So I'm looking to find the first derivative, which makes sense because remember, a derivative gives us the slope of the tangent line, and we're looking for a slope of 0. So if I find the first derivative, again, I've shown some work but not a lot. This is not a section on how to find the derivative. That was last week, so hopefully you're really good at it by now. And what I came up with was a derivative of 9 times the quantity of 9 minus x squared over x to the fourth. Now what I want to do is I want to plug in the value of 3, x equals 3. Now why do I do that? Because I've already sort of cheated, and we won't normally do this. Normally we'll do a little bit more math to actually determine the 3. But you get the idea that if I plug in the 3, then I should get a tangent line with a slope of 0. So if I plug 3 in here, as I have, f prime of 3, notice I get 0, which totally makes sense because that means if I drew the tangent line, the slope of that tangent line would be 0. So of course we want to look at our second type of example, and that is when it's not a nice smooth curved line with a tangent line of 0, but instead a value in which the derivative does not exist. So we're going to take a look at this function, and we're going to, and we don't know how to find the derivative of an absolute value function right now. So we're just going to look at the graph and say, okay, let's find the limit from either direction. So the limit at 0 from the left, again, is just code for what's the slope of the line from the left. It goes through negative 2, 2, or yeah, negative 2, 2, and negative 1, 1, and 0, 0. This slope is negative 1. If I do the same thing from the right, so again, from the right, which means this section of my line, what's the slope of that line? Well, it goes through 0, 0, 1, 1, 2, 2. That slope is 1. Whereas my first slope, again, was negative 1. And if those two don't match up, then obviously there is no limit. So f prime of x does not exist because I can't find the limit at the point 0, 0. So there is no derivative. Again, this agrees with what we are looking at because there's a sharp corner, and that is the other place or position where we might see a relative min or a relative max. So at each relative min or max, or at the relative extrema or extremum, the derivative is either 0 or does not exist. So we just looked at an example of each, where one where it was 0, one where it does not exist. Those x values, as I mentioned previously, are called critical numbers. So critical numbers are important because once we're able to find those, then we're able to determine if it's a min or a max. And that's essentially what we're leading up to by the time we get to the end of section 3.4. So again, the definition of a critical number is that f prime of c equals 0, or f is not differentiable at c, therefore it's a critical number. So again, this would be an example of not differentiable because it's a corner, and this is an example where f prime of c is equal to 0 because the slope is 0 of the tangent line. So it is important to understand that the only time that we can have a relative extrema, a min or a max, is when we do have a critical number. So relative extrema only occur at critical numbers. Now the converse of this is not true. So I can't say that if I have a critical number that it is a min or a max. It's just a potential min or max. So in our next video, it says the following example, which is actually in the next video, we're going to look at an illustration of this. So we're going to look at examples where we have found a critical number, which is what we're going to do next, and that it's not necessarily a min or a max.